You are standing on solid ground. Your feet press against the floor. Gravity pulls you down at 9.8 meters per second squared, the same force that has held every human being to this pale blue dot for 300,000 years. You trust this. You trust that time moves forward at 1 second per second, that when you drop a ball, it falls, that the universe makes sense. But here is the problem. What if I told you that both of those assumptions, the rate at which you fall and the rate at which time passes, are about to betray you in ways that will make you question whether you even exist as a continuous being? What if the answer to how long it takes to fall into a black hole is both a fraction of a second and forever, depending on who you ask? And what if both answers are equally, terrifyingly correct? Let us fall together into the darkest place in the universe, and let us discover that the journey there reveals something unsettling about the nature of time, space, and existence itself. In 1915, Albert Einstein revolutionized our understanding of the universe with his general theory of relativity. He described gravity not as a force pulling objects together, but as a curvature of space-time itself. Imagine a rubber sheet stretched tight. Place a bowling ball in the center, and the sheet deforms. Roll a marble nearby, and it curves toward the bowling ball, not because of any force pulling it, but because it is following the curved surface of the sheet. This is Einstein's genius. Mass bends the fabric of the cosmos, and objects follow the curves that mass creates. The Earth does not pull you down. The Earth curves space-time around it, and you follow that curvature toward its center. The floor stops you only because electromagnetic forces in the atoms of the floor resist your passage. It was elegant, it was beautiful, and almost immediately it predicted something monstrous. Just months after Einstein published his equations, while serving as a soldier on the Russian front during World War I, the German physicist Karl Schwarzschild found something hiding in the mathematics. Sheltering from fierce gunfire, he discovered an exact solution to Einstein's field equations, one that described the curvature of spacetime around a spherical, non-rotating mass. But the solution contained a horror. At a certain radius, a distance that depends only on the mass of the central object, the equations broke down. The curvature became infinite. Time itself seemed to stop. Space and time did something that defied comprehension. Schwarzschild sent his solution to Einstein in December 1915, writing in his letter, "As you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this, your land of ideas." Within 6 months, Karl Schwarzschild would be dead from a rare autoimmune disease contracted at the front. He never knew that he had mathematically predicted one of the strangest objects in the universe. Einstein himself was troubled by the solution. The possibility of a surface where time stops, where space curves back upon itself, where the normal rules of physics simply break down. It seemed impossible. It seemed unphysical. Einstein spent years trying to prove that such objects could not actually form in the real universe. As late as 1939, Einstein published a paper attempting to demonstrate the impossibility of what we now call black holes. He argued that rotating matter would always resist collapse, that centrifugal force would prevent the formation of these monstrous objects. He missed the crucial insight that under the right conditions, gravity would overwhelm all resistance, driving matter past the critical radius from which nothing could escape. He was not alone in his skepticism. For decades, physicists assumed Schwarzschild's singularity was merely a mathematical curiosity, an artifact of idealized symmetry that would never occur in the messy real world. Stars do not collapse perfectly. Matter has angular momentum. Surely, the reasoning went, these imperfections would prevent the formation of such extreme objects. They were all wrong. In 1965, 5 decades after Schwarzschild's discovery, the mathematician Roger Penrose proved something that would eventually earn him the Nobel Prize. Using new techniques in global geometry, sophisticated mathematical tools for analyzing the large-scale structure of space-time, he demonstrated that singularities were not artifacts of perfect symmetry. They were inevitable consequences of gravity itself. Penrose's key insight involved what he called trapped surfaces. Imagine a sphere of light beams emanating outward from a point in space. Normally, this sphere expands as the light travels away from its source. But if enough mass is concentrated in a small enough region, Penrose showed that the gravitational field can be so intense that even light beams directed outward are forced to converge, to fall inward toward the center. Once such a trapped surface forms, Penrose proved, nothing in the laws of physics can prevent a singularity from developing. The collapse is not merely possible, it is mathematically mandatory. This was not philosophy. This was not speculation. This was rigorous mathematics, derived directly from Einstein's equations. The theorem demonstrated that singularities were generic features of general relativity. They would form under almost any realistic conditions of gravitational collapse, regardless of asymmetries or imperfections. The equations of general relativity do not merely allow for these objects, they demand them. Penrose published his proof in Physical Review Letters in January 1965 under the title Gravitational Collapse and Spacetime Singularities. The paper was just 3 pages long, briefed by the standards of theoretical physics, where papers often sprawl across dozens of pages of dense mathematics. But in those 3 pages, Penrose introduced concepts that would reshape our understanding of gravity. The key innovation was his use of global methods, mathematical techniques that analyze the structure of space-time as a whole, rather than examining it point by point. Previous approaches to general relativity had focused on solving Einstein's equations in specific situations, finding the metric at each location. Penrose showed that you could prove general results about entire spacetimes without solving the equations explicitly. His trapped surface concept was the crucial insight. If you could demonstrate that light rays were being focused inward everywhere on a closed surface, then the mathematics guaranteed a singularity somewhere in the future of that surface. The specifics, the shape of the singularity, its location, the path taken to reach it, remained undetermined. But the existence of geodesic incompleteness, paths through spacetime that could not be extended, was proven. The paper changed everything. It showed that singularities were robust predictions of general relativity, not artifacts of idealized assumptions. Any realistic gravitational collapse, with all its asymmetries and imperfections, would still produce a singularity if enough mass was concentrated in a small enough region. In 2020, Penrose was awarded the Nobel Prize in Physics for the discovery that black hole formation is a robust prediction of the general theory of relativity. He was 89 years old, and he had waited 55 years for the recognition. We now know the universe contains billions of these objects. Small black holes form from the collapse of massive stars, those that began their lives with at least 20 times the mass of our Sun. When such stars exhaust their nuclear fuel, gravity crushes their cores past the Schwarzschild radius, and a black hole is born in a cataclysmic supernova explosion. But the universe also contains far more massive specimens. At the center of nearly every large galaxy lurks what astronomers call a supermassive black hole, a monster millions to billions of times more massive than our Sun. We do not fully understand how they formed. Perhaps they grew from smaller black holes that merged over cosmic time. Perhaps they collapsed directly from enormous gas clouds in the early universe. The origin remains one of the great mysteries of astrophysics. The supermassive black hole at the center of our own galaxy, located in the direction of the constellation Sagittarius, is called Sagittarius A, pronounced Sagittarius A star. It contains approximately 4 million times the mass of our Sun, compressed into a region from which not even light can escape. Its event horizon, the boundary of no return, has a radius of about 12 million kilometers. That is roughly 17 times the radius of the Sun. The entire black hole would fit comfortably inside the orbit of Mercury. In May 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius AI, confirming what the mathematics had long predicted. The image showed a bright ring of superheated gas surrounding a dark central shadow, the silhouette of the event horizon itself. Einstein's equations, a century old, had been vindicated once again. The achievement required combining data from radio telescopes spanning the globe, from Hawaii to Chile, from Spain to the South Pole. By synchronizing their observations using atomic clocks, the collaboration created a virtual telescope the size of Earth. The resolution achieved was equivalent to reading a newspaper in New York from a cafe in Paris. The image took 5 years to process. The data volume was so large, several petabytes, that it had to be shipped on hard drives rather than transmitted over the internet. Teams of scientists worked independently to analyze the data, using different algorithms and approaches to ensure that the final image was robust. What they found matched theory perfectly. The shadow of Sagittarius A was almost exactly the size predicted by general relativity. The ring of light showed the expected asymmetry from the Doppler effect as gas orbited the black hole at near light speed. A century of theoretical predictions had been condensed into a single, stunning image. But there are larger monsters still. TON 618 is a quasar, an incredibly luminous object powered by a supermassive black hole devouring vast quantities of gas and dust. Located over 10 billion light-years away, the light we see from TON 618 today began its journey when the universe was less than 3 billion years old. The name comes from the Tonantzintla Observatory in Mexico, where astronomers Braulio Iriarte and Enrique Chavira first catalogued it in 1957 during a survey of faint blue stars. At the time, they thought it as simply a dim blue star in our own galaxy. It would be decades before astronomers understood that TON 618 was not a star at all. It was an entire galaxy, impossibly distant, powered by the most extreme gravitational engine in the known universe. The black hole at TON 618's center is estimated at 40 to 66 billion solar masses. That is not a typo. 66 billion times the mass of our Sun, more massive than all the stars in the Milky Way galaxy combined. To grasp this scale, consider our Sun is about 330,000 times more massive than Earth. The supermassive black hole at the center of our galaxy, Sagittarius A, is about 4 million times more massive than the Sun. TON 618 is more than 15,000 times more massive than Sagittarius A-S. Its Schwarzschild radius, the size of its event horizon, extends over 1,300 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. TON 619's event horizon is more than 40 times the distance from the Sun to Neptune. You could fit our entire solar system inside the event horizon with room to spare, many times over. At such scales, the black hole has earned a new classification, ultramassive. The very terminology had to be invented to describe it. Physicists have debated whether there is a maximum size for black holes, a point where the feeding process that allows them to grow becomes self-limiting. TON 618, with its impossible bulk, challenges our understanding of these limits. The luminosity of the gas falling into TON 618 is equally staggering, about 140 trillion times the luminosity of our Sun. The entire output of the Milky Way galaxy is roughly 100 billion solar luminosities. TON 618's accretion disk outshines our galaxy by a factor of more than 1,000. So the objects are real. The mathematics is certain. The question that remains is, what happens when you fall into one? Let us begin with what seems like a straightforward scenario. You are floating in space, safely distant from a black hole of 4 million solar masses, roughly the size of Sagittarius AA. You have a spaceship, a wristwatch, and a friend who has agreed to stay behind and observe your fate from a safe distance. You also have a decision to make. Do you really want to do this? The question is not rhetorical. Throughout human history, explorers have faced moments of no return, points where the commitment was made and backing out became impossible. Columbus crossing the Atlantic, Armstrong stepping onto the moon. Each journey into the unknown requires a moment of decision, a threshold where theory becomes reality. Your threshold is more absolute than any explorer has ever faced. Once you cross the event horizon, there is no changing your mind, no emergency rescue, no last-minute reprieve. The laws of physics themselves conspire against your return. But you have come this far. You have spent years studying black holes, preparing for this moment. You have made your peace. You are ready. You turn off your engines. You begin to fall. From your perspective, the experience begins normally. You accelerate toward the black hole, pulled by its immense gravity. You feel weightless, as any freely falling object does. This is one of Einstein's key insights. Free fall is locally indistinguishable from floating in empty space. You cannot feel gravity. You can only feel resistance to gravity. When you stand on Earth, you feel the floor pushing up against your feet. Remove the floor, and you feel nothing. The astronauts aboard the International Space Station are not weightless because there is no gravity. They are weightless because they are in free fall, constantly falling toward Earth while also moving sideways fast enough to miss it. And so, falling toward the black hole, you feel at peace. Your internal organs float gently in your chest. Your heartbeat slows. You are, for the moment, comfortable. As you approach, the black hole grows larger in your view. At first, it appears as a dark absence against the star field, a circle of nothing. But as you draw closer, strange optical effects become apparent. The starlight behind the black hole bends around it. Light rays passing close to the event horizon are curved by the intense gravitational field, creating a luminous ring around the dark center. Stars that should be hidden behind the black hole become visible, their light bent around it like water flowing around a stone. This effect is called gravitational lensing, and it was one of the earliest predictions of general relativity. Einstein himself calculated how much the sun would bend starlight passing near its edge, a deflection of about 1.75 arc seconds. In 1919, during a solar eclipse, the astronomer Arthur Eddington measured starlight passing near the sun and confirmed Einstein's prediction. It was this confirmation that catapulted Einstein to worldwide fame. Near a black hole, gravitational lensing becomes extreme. Light rays can orbit the black hole multiple times before escaping, creating multiple images of distant objects. A star directly behind the black hole might produce a ring of light, an Einstein ring, surrounding the dark center. Stars to the side might appear doubled or stretched into arcs. The mathematics of this lensing is beautiful. The Schwarzschild solution predicts a photon sphere at 1.5 times the Schwarzschild radius, a region where light can orbit the black hole in unstable circular paths. Any closer and light is captured, any farther and it escapes. At exactly this distance, photons can circle the black hole indefinitely, though the slightest perturbation sends them spiraling in or flying away. As you approach the event horizon, you would see the photon sphere glowing with accumulated light, radiation that has been orbiting the black hole, trapped in its gravitational web, slowly leaking away or falling in. This gravitational lensing grows more extreme as you approach. The distant stars behind the black hole appear distorted, stretched into arcs and rings by the curvature of space-time. The universe wraps around the black hole's shadow, creating a halo of warped starlight, the last image of the cosmos you will ever see intact. And then you cross the event horizon. Here is the first terrifying revelation. You notice nothing. There is no barrier, no membrane, no flash of light or rumble of thunder, no sign that says event horizon, point of no return. You pass through it as easily as crossing an imaginary line on a map. The event horizon is not a surface in any physical sense. It is merely a boundary defined by causality, the mathematical point beyond which all paths, even those of light itself, lead inward. Inside the horizon, there is no trajectory, no rocket burn, no conceivable maneuver that can take you outward. Not because you lack the power, but because outward no longer exists as a direction. You have passed the point of no return, and you did not even feel it happen. From your perspective, time continues normally. Your watch ticks forward at 1 second per second. Your heart beats, your thoughts flow. You look around, and the universe still exists. Distorted, yes, but visible. Light from outside the black hole can still reach you, falling inward along with everything else. You could, in principle, continue observing the stars outside the black hole for the remainder of your journey. They would appear blue-shifted, their light compressed to higher frequencies, shorter wavelengths as you plunge deeper into the gravitational well. For a supermassive black hole like Sagittarius AA, the journey from the event horizon to the singularity takes roughly 16 to 30 seconds of your personal time. Half a minute. You could count the seconds on your fingers. That is how long it takes you to fall into a black hole. But here is the problem. While you are plunging toward the singularity, counting off your final 30 seconds of existence, let us check in with your friend who stayed behind. She is hovering at a safe distance, perhaps a few hundred Schwarzschild radii from the black hole, watching you through an incredibly powerful telescope. What does she see? She sees you approach the event horizon. She sees you slow down. And then, impossibly, she sees you stop. You do not cross the horizon. You hang there, frozen at the boundary of the black hole, forever suspended in the moment before oblivion. As she watches, your image changes. It grows redder, the light from your body stretched to longer and longer wavelengths by the extreme gravitational redshift. Your movements slow to a crawl, then to imperceptibility. The intervals between your heartbeats stretch to hours, then days, then years. Eventually, you fade from view entirely, not because you have crossed the horizon, but because the light escaping from your position has been stretched beyond detection. The photons leaving your body have lost so much energy climbing out of the gravitational well that they have redshifted into radio waves, then into infrared, then into wavelengths so long that no instrument can detect them. From her perspective, you will never fall in. The event horizon is a place where time, as measured by distant observers, comes to a complete stop. She could watch for 1 billion years, for 1 trillion years, for the entire remaining lifespan of the universe. She would never see you cross that threshold. According to her measurements, you are eternally suspended at the edge of the void. This is not an illusion. This is not a failure of her instruments. This is not a trick of perspective. Both experiences are equally valid in Einstein's relativity. You experience a 30-second plunge to annihilation. She experiences watching you freeze forever at the edge of eternity. 2 truths, 1 universe. Let that sink in. The technical explanation for this paradox involves a distinction that lies at the heart of general relativity, the difference between what physicists call proper time and coordinate time. These concepts sound abstract, but they have concrete, measurable consequences. Every GPS satellite in orbit must account for them. Every precision measurement in physics must consider them. They are not philosophical curiosities, but physical realities. Proper time is the time you experience on your own clock, the subjective duration of your existence as measured by the watch on your wrist. It is the time between events as experienced by an observer who is present at both events. Mathematically, it is defined by integrating along your world line through space-time. Coordinate time is the time measured by distant observers using their own clocks. It is defined with respect to a coordinate system, a way of labeling points in space-time that extends across large distances. Different coordinate systems give different coordinate times for the same physical events. In flat space-time, far from any massive objects, these 2 concepts roughly coincide. Your watch and your friend's watch tick at roughly the same rate, but near a black hole, the discrepancy becomes extreme. The mathematics is precise. In the Schwarzschild solution, the equations describing a non-rotating black hole, the coordinate time for an object to reach the event horizon approaches infinity. The proper time remains finite. Both calculations are correct. Neither is more real than the other. This is what physicists mean when they say that simultaneity is relative in general relativity. There is no universal now that stretches across space-time. 2 observers can disagree about whether events are simultaneous. about how much time has passed between events, even about the order in which events occurred, and both can be correct according to their own reference frames. You experience crossing the event horizon. Your friend never observes you crossing it. Both statements are true. Both describe the same physical reality. We are not talking about perception. We are not talking about the limitations of observation. We are talking about the fundamental nature of time itself. Time is not what you think it is. It does not flow uniformly from past to future. It does not tick at the same rate for all observers. It is elastic, stretchable, capable of running at different speeds in different places. Near a black hole, this elasticity becomes extreme. Time at the event horizon, from the perspective of distant observers, stops entirely. 30 seconds of your experience maps onto an eternity of theirs. And this is where it gets terrifying. But we are not done with the strangeness. Let us follow you past the event horizon and into the interior of the black hole. Here, the mathematics reveals something even more disturbing. Outside the black hole, space has 3 dimensions. You can move left or right, forward or backward, up or down. These directions are all equivalent in the sense that you can traverse them freely. You can go toward the black hole or away from it as you choose. Time, in contrast, has a single dimension, and it flows in only one direction. You cannot choose your motion through time. You can only move forward from past to future at a rate of 1 second per second. Inside the black hole, these roles exchange. The radial coordinate r, which outside the black hole represents your distance from the center, becomes time-like, and the time coordinate t becomes space-like. This is not a metaphor. This is not an analogy. The mathematics of general relativity describes a genuine exchange of the fundamental properties of space and time inside the event horizon. The technical term for this exchange involves the signs of metric coefficients, the mathematical objects that define distances and durations in curved space-time. Outside the event horizon, the time coefficient is negative in the standard convention, indicating that motion along the time direction is fundamentally different from motion along spatial directions. Inside the horizon, this coefficient becomes positive, and the radial spatial coefficient becomes negative. If this sounds abstract, think of it this way. The property that makes time different from space, the property that forces you forward into the future, that prevents you from traveling backward, that makes the flow of time fundamentally unlike the freedom of spatial motion. That property gets transferred to the radial direction inside the black hole. Think about what that implies. Outside the black hole, you can move freely in any spatial direction. You can approach the black hole or flee from it, but you cannot choose your direction in time. You can only move forward toward the future. Inside the black hole, this relationship inverts. The time coordinate to become something you can, in principle, traverse in either direction. It becomes a spatial dimension. But the radial coordinate r becomes locked. You can only move in one direction, inward, toward the singularity. The singularity is no longer a place at the center of the black hole. It is a moment in your future. Just as surely as tomorrow will arrive, the singularity will arrive. You cannot avoid it any more than you can avoid next Tuesday. It is not somewhere you fall to. It is someone you fall toward. Every path you could possibly take, no matter how you fire your rockets or twist your trajectory, ends at the singularity. Not because you cannot move fast enough to escape, but because every direction in space-time points there. The geometry of the interior is such that all roads lead to the singularity. Here is a cruel irony that the mathematics reveals. Suppose that immediately upon crossing the event horizon, you fire your rockets at maximum thrust, pointing away from the singularity. You might think this would slow your descent, buying you precious seconds of additional life. It does the opposite. In the bizarre geometry inside the black hole, firing your rockets to resist the fall actually hastens your arrival at the singularity. The optimal strategy for maximizing your survival time is to do nothing, to fall freely without resistance. This counterintuitive result was demonstrated rigorously by Geraint Lewis and Juliana Kwan at the University of Sydney in a paper titled No Way Back: Maximizing Survival Time Below the Schwarzschild Event Horizon. The mathematics is clear. People in freefall experience the maximum proper time. Struggling against the black hole only makes your death arrive sooner. What awaits you at the singularity? Here, our physics breaks down entirely. The singularity is a point of infinite density, infinite curvature, a place where Einstein's equations produce infinity after infinity. The curvature of space-time becomes so extreme that the very concepts of space and time lose their meaning. Physicists call this a geodesic incompleteness. Your world line, the path you trace through space-time, simply ends, not because you hit something, but because space-time itself ceases to exist. There is no after the singularity. There is no beyond it. The world line terminates, and the theory has nothing further to say. We do not know what happens at a singularity. General relativity, our best theory of gravity, cannot describe it. The theory predicts its own failure. Whatever lies at the center of a black hole requires a quantum theory of gravity that we have not yet discovered. Roger Penrose himself, whose singularity theorem demonstrated that these points are inevitable, has proposed what he calls cosmic censorship, the conjecture that all singularities are hidden behind event horizons, forever shielded from the rest of the universe. If true, the singularity's violations of known physics remain locked away, unable to contaminate the external universe. But this is a conjecture, not a theorem. We do not know if cosmic censorship holds universally. We do not know what happens when general relativity meets quantum mechanics at the singular point. The center of a black hole remains one of the deepest mysteries in all of physics. But before you reach that ultimate unknown, you will face something more immediate and visceral: spaghettification. The term was coined by Stephen Hawking in his best-selling book, A Brief History of Time, and it describes exactly what it sounds like. As you approach the singularity, the tidal forces, the difference in gravitational pull between different parts of your body, increase without limit. Tidal forces are not unique to black holes. They exist wherever gravity exists. The key is that gravitational strength varies with distance. Objects closer to a massive body feel stronger gravity than objects farther away. This difference, this gradient in gravitational pull, is what creates tides. To understand tidal forces, think about the Moon and Earth's oceans. The Moon's gravity pulls more strongly on the side of Earth, nearest to it, and less strongly on the far side. This difference in gravitational pull, not the absolute strength of the Moon's gravity, creates the tides. The near side of Earth is pulled toward the Moon more than the center, and the center is pulled more than the far side. The result is a stretching of Earth along the line, connecting it to the Moon. The effect is subtle on Earth. The tidal acceleration from the Moon is about 1/10,000,000th of Earth's surface gravity. You cannot feel it, but the oceans can. They slosh and surge in response to this gentle differential pull. Near a black hole, this differential effect becomes extreme. If you are falling feet first toward the singularity, your feet are closer to the center of mass than your head. Gravity pulls more strongly on your feet. This difference stretches you vertically, like taffy being pulled at both ends. At the same time, because your left side and right side are falling toward the same central point, they are pulled toward each other. You are compressed horizontally while being stretched vertically. The net result is spaghettification. You are drawn out into a long, thin strand, like a piece of spaghetti being extruded through a pasta maker. For a stellar mass black hole, one formed from the collapse of a single massive star, perhaps 10 to 50 times the mass of our Sun, spaghettification is lethal long before you reach the event horizon. The tidal forces become fatal at hundreds of kilometers from the center, well outside the Schwarzschild radius. According to calculations from Gravitation by Meissner, Thorne, and Wheeler, the definitive textbook of general relativity, an 8 solar mass black hole would have fatal tidal forces at a radius of about 400 kilometers. The Schwarzschild radius of such a black hole is just 24 kilometers. You would be stretched into atoms long before you ever reach the event horizon. But for supermassive black holes, the calculus changes dramatically. The tidal force at a given distance from a black hole scales as the mass divided by the cube of the radius. The Schwarzschild radius, meanwhile, is directly proportional to mass. This means that larger black holes actually have weaker tidal forces at their event horizons. For Sagittarius AR, with its 4 million solar masses, the tidal forces at the event horizon are negligible, less than what you experience standing on Earth. You could cross the event horizon without noticing any significant stretching. You would have time to contemplate your fate. You would have those 30 seconds of peaceful freefall before the tidal forces caught up with you. For TON 618, with its 60 billion solar masses, the journey would be even more leisurely. The tidal forces at its enormous event horizon would be imperceptible. You could fall for hours of your proper time before the stretching began. But eventually, no matter how large the black hole, the tidal forces catch up. As you approach the singularity, the differential gravity increases without bound. Your body, designed to withstand the mild tidal forces of Earth's modest gravity, cannot survive. First, the stretching becomes uncomfortable, then painful. Then your tissues begin to tear. Your spine elongates. Your circulatory system fails as your heart can no longer pump blood through your increasingly extended body. You are pulled apart at the cellular level, then the molecular level, then the atomic level. The atoms that once composed you are drawn into a stream of particles, falling toward a point of infinite density. And then, we do not know. The physics ends where the singularity begins. Physicists have struggled for over a century to resolve the paradoxes of black holes. Several approaches have been attempted. None have fully succeeded. The first major breakthrough came in 1974, when Stephen Hawking made a discovery that shocked the physics community. Black holes are not entirely black. Hawking was 32 years old, already famous for his work on singularities with Roger Penrose. already struggling with the motor neuron disease that would eventually confine him to a wheelchair. He was attending a conference in Oxford when he presented a calculation that seemed impossible. By combining quantum mechanics with general relativity, two theories that had resisted unification for decades, Hawking found that quantum effects near the event horizon cause black holes to emit a faint thermal radiation. This radiation, now called Hawking radiation, causes black holes to slowly lose mass and eventually evaporate. The reaction from the physics community was initially skeptical. Black holes, by definition, do not let anything escape. That was the whole point. The event horizon was supposed to be a one-way membrane, a boundary of absolute darkness. But Hawking's calculation was meticulous, and it held up under scrutiny. The radiation was real, at least in theory. It emerged from the peculiar properties of quantum fields in curved spacetime, from the way the vacuum itself behaves near an event horizon. The mechanism is subtle and involves the peculiarities of quantum field theory in curved spacetime. In simplified terms, the vacuum of space is not truly empty. Quantum mechanics describes a seething foam of virtual particle-antiparticle pairs, constantly appearing and annihilating throughout space. Near the event horizon, the intense gravitational field can separate these virtual pairs before they annihilate. One particle falls into the black hole, the other escapes into space. The escaping particle carries energy away from the black hole, effectively reducing its mass. This process is incredibly slow. The temperature of a black hole's Hawking radiation is inversely proportional to its mass. Larger black holes are colder. A black hole the mass of our Sun would have a temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that permeates space. Such a black hole would take approximately 10 almost 67 years to evaporate, a 1 followed by 67 zeros. The current age of the universe is about 1.4 kex 10 to 10 years. The evaporation timescale is so vast that it is effectively meaningless on any human or even cosmic timescale. But the principle is profound. Black holes are not eternal. They are thermodynamic objects with temperature, entropy, and a finite lifespan. Given enough time, cosmologically vast amounts of time, every black hole will eventually evaporate, shrinking and heating until it vanishes in a final burst of radiation. This should, in principle, resolve the paradox of things being frozen at the horizon forever. Eventually, the black hole itself will evaporate, and whatever was falling in will... what? This leads to one of the deepest unsolved problems in physics, the black hole information paradox. Here is the problem. Quantum mechanics demands that information is conserved. The quantum state of any system, no matter how complex, can in principle be reconstructed from its past states or predicted from its future states. Information cannot be created or destroyed. It can only be transformed. But if a black hole absorbs matter, with all its information about quantum states, particle types, and configurations, and then evaporates through Hawking radiation that is purely thermal, purely random, carrying no information about what fell in, then information appears to be destroyed. A book that falls into a black hole is not merely incinerated. It is transformed into random radiation that contains no memory of the book's contents. Not even in principle could the book be reconstructed from the Hawking radiation. This contradicts a fundamental principle of quantum mechanics. Something must be wrong with our understanding. For decades, physicists have proposed various resolutions. Perhaps the information escapes in subtle correlations in the Hawking radiation, correlations so delicate that they are practically undetectable, but preserve the information in principle. Perhaps the information is stored in some remnant when the black hole finally evaporates, a tiny, stable object that holds the memories of everything that fell in. Perhaps the information is encoded on the event horizon itself in a holographic pattern that can in principle be decoded. In 2019, physicists proposed a radical solution involving quantum entanglement and what they called islands of spacetime. Using calculations from string theory and quantum information theory, they suggested that portions of the black hole's interior could be reconstructed from information in the Hawking radiation, as if the interior and the radiation were secretly the same thing, connected by quantum entanglement. The details are technical and controversial, but the implication is stunning. What falls into a black hole might not be truly lost. The information might escape, scrambled beyond recognition, but preserved in principle. Another proposal, called the firewall hypothesis, suggests a more violent resolution. Perhaps the event horizon is not the smooth, undetectable boundary that general relativity describes. Perhaps instead, it is a seething wall of high-energy particles that would incinerate anything attempting to cross. If the firewall exists, there is no interior to the black hole in the usual sense. Nothing survives the crossing. The problem of what happens inside becomes moot because there is no inside, just annihilation at the boundary. The firewall hypothesis resolves some paradoxes, but creates others. It violates the equivalence principle, the fundamental insight that freely falling observers should not experience anything special at a gravitational horizon. Einstein's beautiful principle, which underlies all of general relativity, would have to be abandoned. The honest answer is that we do not know. We have equations that work beautifully in certain regimes and fail utterly in others. The marriage of general relativity and quantum mechanics, required to truly understand what happens at the event horizon and the singularity, remains one of physics' greatest unsolved problems. There is one more possibility that emerges from the mathematics, one that sounds like science fiction, but appears naturally in the equations. Wormholes. Real black holes, unlike the idealized Schwarzschild solution, rotate. A rotating black hole is described by the Kerr metric, discovered by Roy Kerr in 1963. And the Kerr solution contains something extraordinary. Instead of a point singularity at the center, a rotating black hole has a ring singularity, a circle of infinite curvature. And the mathematics suggests that this ring is not necessarily a dead end. Fall through the ring, and you might emerge somewhere else. Perhaps another region of our universe. Perhaps another universe entirely. Perhaps a white hole, a time-reversed black hole that spits out matter instead of absorbing it. These possibilities emerge directly from Einstein's equations. The full mathematical solution for a rotating black hole includes regions of space-time that are causally disconnected from our own, inaccessible except by passing through the black hole's interior. But here is the problem with this escape route. As you approach the inner horizon of a rotating black hole, a second boundary that lies inside the event horizon, you encounter an effect called infinite blue shift. All the light that has ever fallen into the black hole for all of cosmic history accumulates at the inner horizon. The radiation is compressed, blue-shifted, concentrated into an infinitely energetic beam. You would be fried by hard radiation long before you reach the would-be wormhole. Moreover, recent calculations suggest that the inner horizon itself is unstable. The accumulation of infalling radiation causes the curvature at the inner horizon to grow without bound, transforming it into a singularity in its own right. The escape hatch, if it ever existed, has been welded shut by the physics of the black hole's own evolution. Physicists Paul Chesler, Ramesh Narayan, and Eric Curiel, affiliated with Harvard's Black Hole Initiative, have studied this problem using sophisticated numerical simulations. They found that for realistic rotating black holes, a null singularity forms at the inner horizon, and a space-like singularity eventually forms at the center, much like the simple Schwarzschild case. Some theorists speculate about wormholes stabilized by exotic matter with negative energy density, hypothetical materials that might hold the throat open against collapse. Others invoke quantum gravity effects that might smooth out the singularities and render the passage survivable. These remain speculative. Interesting possibilities explored in theoretical papers, but not predictions we can test with current technology or knowledge. For now, the verdict of physics is clear. If you fall into a black hole, you are not coming back. There is a final irony worth contemplating. The black hole that will one day consume you, if you ever make that fateful journey, will itself eventually die. Stephen Hawking showed us that black holes are not eternal. Through the slow leak of Hawking radiation, every black hole will eventually evaporate. The supermassive black holes that dominate galaxy centers today will persist for unimaginable spans of time, 100 years or more, but they will not last forever. Eventually, the last black hole in the universe will shrink to nothing, releasing its final burst of radiation, and the cosmos will enter a new phase, the dark era, when only cold particles drift through an ever-expanding void. In the very long run, black holes are not the end of the story. They are a phase, the universe's way of storing mass energy in its most compact form, preserving it against the dilution of cosmic expansion, before finally releasing it back into the void. But that is a timescale beyond human comprehension, beyond even the comprehension of any species that might follow us. For all practical purposes, for all purposes that matter to beings like us, black holes are eternal. They are the closest thing to permanence that the universe allows, and they remain, after all these years of study, fundamentally mysterious. We know their surfaces. We can predict their shadows. We can calculate the time it takes to fall through them. But we cannot see their hearts. We cannot know what happens at the singularity. We cannot reconcile the physics of their exteriors with what must happen in their interiors. They keep their secrets well. So what does it all mean? What do we take away from this journey into darkness? You have learned that the trip into a black hole takes 30 seconds or forever, depending on who measures it. You have learned that space and time exchange roles at the event horizon, that the singularity is a moment rather than a place. The tidal forces will stretch you into atomic spaghetti. You have learned that physics itself breaks down at the core, that paradoxes pile upon paradoxes, and that our deepest theories admit their own limitations. This could be cause for despair. The universe contains objects that annihilate everything that enters them, that mark the boundary where our understanding collapses. that represent the ultimate finality. But consider another perspective. The black hole at the center of our galaxy has been there for billions of years. It has shaped the formation of the Milky Way, flinging stars into their orbits, governing the dance of matter across 100,000 light years. The supermassive black holes at the centers of galaxies regulate star formation, drive galactic evolution, and seed the conditions that would eventually produce solar systems, planets, and life. Without black holes, galaxies as we know them might not exist. The very spiral structure of the Milky Way, the distribution of stars that includes our Sun, the cosmic environment that allowed Earth to form, all of these bear the fingerprints of the supermassive black hole lurking at the galactic center. And the paradoxes of black holes are not weaknesses in physics. They are signposts pointing toward deeper truths. Throughout the history of science, the most profound discoveries have come from confronting apparent paradoxes, from places where our theories gave contradictory or impossible answers. Maxwell's equations predicted that the speed of light should be constant regardless of the observer's motion, a paradox that led Einstein to special relativity, the ultraviolet catastrophe, a calculation that suggested heated objects should emit infinite energy at short wavelengths, led Max Planck to discover quantum mechanics. The black hole information paradox, the clash between general relativity and quantum mechanics revealed most dramatically at the event horizon, is precisely the kind of creative tension that has historically driven scientific revolutions. Somewhere in the attempt to reconcile these two great theories lies a deeper truth about the universe: quantum gravity, a theory that describes space-time at the Planck scale, at the heart of black holes, at the first instant of the Big Bang, a framework that reveals the true nature of space and time. We do not have it yet, but the paradoxes tell us where to look. In 1783, the English natural philosopher John Michell first imagined dark stars, objects so massive that light could not escape their gravity. He reasoned correctly that if enough mass were concentrated in a small enough space, the escape velocity would exceed the speed of light. Michel had no equations to prove his intuition. He had no way to calculate the radius of such an object, no method to determine whether they could actually form. But he imagined them. 240 years later, we have photographs. The Event Horizon Telescope collaboration, a global network of radio observatories spanning from Hawaii to Spain, from the South Pole to Chile, combined their signals to create a virtual telescope the size of Earth. The data processing required years of painstaking work, with teams of scientists across multiple continents independently analyzing the results to ensure their robustness. And in 2019, they released the first image of a black hole, the supermassive object at the center of the galaxy 87, 55 million light-years away, containing 6.5 billion solar masses. 3 years later, they imaged Sagittarius A's, the black hole at the center of our own galaxy. The progression from imagination to mathematics to observation represents something profound about human capability. We are a species that emerged on the African savanna, evolving to track prey and avoid predators, to navigate seasons and social hierarchies. Nothing in our evolutionary history prepared us to understand objects that bend space-time, that stop time at their surfaces, that represent the literal end of space and time at their centers. And yet we understand them, imperfectly, incompletely. but we understand them. We have written down equations that describe the curvature of space-time around these objects. We have calculated how long it takes to fall in, how the tidal forces grow, what a distant observer would see. We have built telescopes to image them, detectors to sense the gravitational waves when they collide, supercomputers to simulate their formation and evolution. The black hole does not care about your watch. It does not care about your friend's watch. It does not even acknowledge the distinction between space and time that you have used to navigate your entire existence. It simply warps reality according to the equations Einstein wrote down over a century ago, equations that continue to be confirmed by every observation we make. Perhaps the most profound lesson of the black hole is this: the universe is under no obligation to make sense to beings who evolved on African savannas to track prey and avoid predators, that it makes any sense at all, that mathematics, this abstract human creation, describes the curvature of space-time with exquisite precision, is itself a kind of miracle. We are made of matter that was forged in the hearts of ancient stars. Those stars, in turn, were born from gas clouds shaped by the gravity of black holes. The supermassive black holes at the centers of ancient galaxies drove jets of material into intergalactic space, seeding distant regions with the heavy elements that would eventually form planets and people. You exist, in some sense, because black holes exist. The very atoms in your body bear the imprint of these cosmic monsters. And now you understand a little better what lies inside them. Not the final answer, that remains unknown. Not the resolution of the paradoxes that awaits a future generation of physicists. But the questions. The beautiful, terrifying questions that have driven physics for over a century and will continue to drive it for centuries to come. How long does it take to fall into a black hole? 30 seconds. Forever. Both true, both real. Welcome to the universe as it actually is, stranger than we imagined, stranger than we can imagine, and yet somehow, against all odds, comprehensible to minds made of stardust. But wait, there is one more thing you should know. In 2020, when Roger Penrose was awarded the Nobel Prize for his 1965 Singularity theorem, he shared the prize with two observational astronomers, Reinhard Genzel and Andrea Ghez. Their achievement was complementary to his. While Penrose proved mathematically that black holes must form, Genzel and Ghez spent decades proving that one actually exists at the center of our galaxy. For over 25 years, using some of the world's largest telescopes, Genzel and Ghez independently tracked the orbits of stars near the galactic center. They watched stars whip around an invisible point at incredible speeds, up to 3% of the speed of light. They measured orbits that take only 16 years to complete, bringing stars perilously close to something enormously massive and extraordinarily compact. Their measurements left no room for doubt. Whatever lurks at the center of our galaxy contains 4 million solar masses, compressed into a region smaller than our solar system. No known object besides a black hole could be so massive and so compact. The mathematics of Penrose and the observations of Genzel and Ghez converged on the same conclusion. Black holes are real. This convergence of theory and observation, of abstract mathematics and meticulous measurement, represents the scientific method at its finest. Einstein imagined how gravity might bend space-time. Schwarzschild solved the equations. Penrose proved that singularities were inevitable. And Genzel and Ghez Watch the stars dance around one, each generation built on the last. Each approach, theoretical, mathematical, observational, contributed something essential. And together, they revealed a truth about the universe that no single method could have uncovered alone. Let us return one final time to the question that started our journey. How long does it take to fall into a black hole? The answer, we now know, depends on who is asking. For you, the intrepid traveler plunging into the void, the answer might be 30 seconds, perhaps a few hours, if you choose an especially large supermassive black hole. A finite, measurable, countable span of proper time, the ticking of your own wristwatch, before you reach the singularity. For your friend watching from a safe distance, the answer is eternity. You will never cross the event horizon. You will hang there forever, growing dimmer and redder, frozen at the boundary between existence and oblivion. For the universe at large, the answer might be both and neither. The event horizon is not a moment in time that all observers agree upon. It is a feature of space-time geometry, experienced differently by different observers, revealing itself only through its effects on light and matter. This is what Einstein's relativity teaches us. There is no universal time. There is no cosmic clock that ticks at the same rate everywhere. Duration is not an absolute property of the universe. It is a relationship between observer and observed, between clocks and gravitational fields, between the geometry of space-time and the world lines traced through it. We live our lives as if time was simple. We set appointments, catch trains, celebrate birthdays. We talk about the past and worry about the future as if these were universal categories, shared equally by all observers throughout the cosmos. But they are not. Time near a black hole runs differently than time on Earth. Time in intergalactic space runs differently than time in the gravitational well of a galaxy cluster. Every object in the universe experiences its own proper time, its own subjective duration, and these do not necessarily agree. The black hole does not create this strangeness, it merely reveals it. The flexibility of time, its dependence on gravity and motion, is present everywhere in the universe. We do not notice it because we live in a weak gravitational field, moving at slow speeds compared to light. But the effects are real, and they accumulate. The GPS satellites orbiting Earth must account for relativistic time dilation. Their clocks, sitting in weaker gravity than clocks on the surface, tick faster by about 38 microseconds per day. Without correction for this effect, GPS navigation would accumulate errors of several kilometers per day. Time dilation is not a curiosity confined to black holes. It is a feature of the universe we inhabit, measurable with atomic clocks, essential to the technologies we use every day. There is something almost religious in the contemplation of black holes. They represent the edge of knowledge, the boundary of the comprehensible, the place where our equations and our intuitions both fail. They are cosmic horizons in a deeper sense than the astronomical one, horizons of understanding, beyond which lies terra incognita. Throughout human history, we have pushed back the boundaries of the known. We mapped the continents, charted the stars, split the atom, sequenced the genome. Each frontier revealed new mysteries beyond it, not answers, but deeper questions. The black hole represents the ultimate frontier. Not because nothing lies beyond it. We know that the interior exists, that matter falls through, that time continues for the infalling observer. But because We cannot retrieve any information from beyond that boundary. We cannot send messages. We cannot make measurements. We cannot verify our theories. Everything we know about the interior of black holes is inference, extrapolation, mathematical prediction. We trust these predictions because general relativity has passed every test we have devised outside the event horizon. We believe that the same equations apply inside, but we cannot confirm it. This is a new kind of scientific boundary. In the past, we could always imagine ways to test our theories, to gather evidence, to revise our understanding based on observation. The black hole's interior is forever hidden. Whatever truths it contains are locked away from us, not by practical limitations that technology might overcome, but by the fundamental structure of space-time itself. And yet we theorize, we calculate, we imagine. Human minds evolved to navigate the African savanna, turn their attention to objects that could fit inside a city, yet weigh more than the sun. We write equations that describe the curvature of space-time, the exchange of space and time, the inevitable march toward singularity. This is what we are. This is what we do. We are the universe trying to understand itself, using tools fashioned from matter and energy, powered by nuclear reactions in the hearts of stars, gazing back at the cosmic processes that created us. The physicist John Wheeler, who popularized the term black hole in the 1960s, once said, "Space-time tells matter how to move. Matter tells space-time how to curve." This elegant summary captures the essence of general relativity, the beautiful feedback loop between geometry and physics that governs the cosmos. Black holes represent the extreme limit of this feedback. So much matter, so concentrated, tells space-time to curve so severely that the curvature itself becomes the dominant feature. The matter that formed the black hole is gone, crushed into the singularity, no longer distinguishable from the space-time geometry it created. What remains is pure curvature, pure geometry, a persistent scar in the fabric of the cosmos. From this perspective, a black hole is not really a thing in the usual sense. It is a region of space-time, a piece of geometry, a structure in the fabric of reality itself. The event horizon is not a surface, but a boundary in the mathematical description of space-time. The singularity is not a point, but a limit where our description breaks down. This is perhaps the deepest lesson the black hole teaches us. Matter and space-time are not separate things. They are aspects of a single reality, woven together by gravity, distinguishable in normal conditions, but united at the extreme. Quantum mechanics suggests something similar about matter and energy, that particles are excitations in underlying fields, not fundamental entities in their own right. The emerging picture of physics points toward a universe that is, at its deepest level, made of relationships and patterns rather than stuff and things. The black hole, that destroyer of matter, that eraser of information, might be trying to tell us something important about the nature of reality. We are still learning to listen. You started this journey standing on solid ground, your feet pressed against the floor. Gravity pulled you down. Time moved forward at 1 second per second. All of those things were true. All of them were approximations. The floor beneath you is mostly empty space. Atoms held apart by electromagnetic forces, solid only because your atoms cannot pass between theirs. Gravity is not a force, but a curvature of space-time, and you are in constant freefall toward Earth's center, stopped only by the floor's resistance. Time moves at 1 second per second only relative to your own clock. Other clocks in different gravitational fields or different states of motion tick at different rates. The universe you inhabit is stranger than the one you thought you knew. It runs on rules that your intuition cannot grasp directly, rules that must be expressed in the abstract language of mathematics to be captured at all. And at the center of galaxies, at the end of massive stars, at the heart of the most violent events in the cosmos, those rules produce objects that challenge everything we think we understand about space, time, matter, and existence. Black holes. You exist in some sense. Because black holes exist, the very atoms in your body bear the imprint of these cosmic monsters. The carbon in your cells, the iron in your blood, the calcium in your bones. All of these heavy elements were forged in the cores of ancient stars, then scattered across the cosmos when those stars exploded. Some of those explosions created black holes. Some of those explosions were triggered by interactions with existing black holes. The cycles of stellar birth and death, gravitational collapse and explosive rebirth have been ongoing for billions of years, and black holes have been part of that cycle from the beginning. The supermassive black holes at the centers of galaxies played an even more direct role in your existence. In the early universe, these cosmic engines drove powerful jets of radiation and matter into intergalactic space, heating the surrounding gas and regulating the rate of star formation. Without this feedback, galaxies might have formed too quickly, burning through their gas in a few 100 million years rather than the billions of years required for planets to form and life to evolve. We are children of the stars and grandchildren of the black holes that shape those stars' environments. Our very existence is proof that the universe, for all its terrors, is capable of producing beings who can contemplate its deepest mysteries. How long does it take to fall into a black hole? 30 seconds. Forever. Both true, both real. The answer depends on who you ask, on where they stand, on how they measure time. It depends on the curvature of space-time, on the distinction between proper and coordinate time, on the fundamental nature of the universe itself. And it depends on you, on your willingness to ask the question, to follow the mathematics wherever it leads, to accept answers that defy intuition and challenge everything you thought you knew. The asking, the ability to formulate the question, to calculate the answer, to comprehend the paradox, that belongs to us. That is what makes us human. We are the universe, contemplating itself, falling into its own depths. Welcome to the universe.